Welcome back all of you. In the last class, we discussed about pulse field gradients. In fact, last two classes we discussed a lot about pulse field gradients, and we discussed how the field gradient is generated, what the gradient does, what happened to the spins in the gradient coil above the center 0 and below, what will happen, how the spin species, and finally how completely they get dephased and without giving rise to any signal. And then we also discuss there is a way we can reverse this, because z rotation can be reversed by applying the counteracting gradient with the opposite, exact equal and opposite sign. And we also discuss a lot about how we can use this gradient to choose a particular coherence pathway. And we took the example of homonuclear case. When I have a gradient pulse just before 90-degree pulse, call it G1, and I have a gradient pulse just after 90-degree pulse, call it G2. Then we calculate what is the phase acquired during G1 by the spins, phase acquired, that is it was given by a simple expression minus P into gamma into all the Gz into T, that we knew that. And then work out the phase acquired for the during the gradient G2 also. Totally we, of course both of them come with a negative sign, minus phase acquired is minus of P1 into those terms. Similarly, phase acquired during G2 also minus P2 into those terms, gamma into etc. terms. I said the refocusing condition to make sure that the signals are detectable, the total phase acquired phi 1 plus phi 2, that is during gradient 1 and gradient 2, should be equal to 0. We equated that and did some mathematical jugglery and found out what is the ratio of G1 and G2, for example G2 T2 over G1 T1 or vice versa, and what is the ratio of gammas we get. Based on the ratios of the gammas, we could even calculate what is the G1 G2 ratio we require. Keeping T1 equal to T2, that is the duration of the gradient exactly same, we can get G1 by G2 because I know gamma. So very simple. And when we worked out for the homonuclear case, it was 1 over 1 minus some number which we worked out, especially even if you take a heteronuclear case or no problem, homonuclear case also. We worked out what is the ratio. Heteronuclear case, of course, only thing is difference is coherence. You have to consider for both the spins during both the gradients. For example, gradient 1, what is the pathway selected for spin I? What is the pathway selected for spin S during G1? Use that, calculate the total phase for that, for both. Similar operation you do for calculation. What is the phase acquired during G2 by I spin and also by S spin? Again, for refocusing condition, take the total phase, equate it to 0 and do simple mathematical jugglery. We can find out what is the ratio of G1 and G2 required to select the particular pathway. But in this case it is slightly different because gammas are different for heteronuclear case. We understand. Homonuclear case gammas were same and the equation turned out to be a very simple one, and we got some number like G1 into G1 equal to minus of 1:2 or 1:-2 like that. Here you get some fraction because gammas are different. With that we can go further, little bit, 1 or 2 more applications of gradient we discuss quickly without going into the more details because it is taking a lot of time. Because I come back to gradient little bit after 2D to find out whether how we can apply gradients to select the particular pathway. We can discuss little bit more also. So hence quickly I will go through some 1 or 2 simple applications of gradients. What we can do using gradients. Gradients can be used as the refocusing pulses. What is the meaning of refocusing pulse? A perfect 180-degree pulse, what it does? I told you even earlier we discussed 180 pulse will invert the population. When it inverts the population, means it reverses the coherence order. For example, this is the plus P before 90-degree pulse or 180 pulse. Before 180 pulse, I have a coherent order P chosen here. And then I have a gradient G before 180. Then after applying 180 pulse, then the coherent order immediately after that will become minus P. That is what known to us, because 180 pulse always invert the populations. When it inverts the population, it reverses the coherence order. Plus p will become minus p. If this were to be minus p and here plus p, it gets reversed. Okay. So it inverses the coherence order. But what will happen if 180 pulse is not perfect? Let us say it is not exact 180, it is 178 degree or 182 degree or 181 degree, like that. Then what is going to happen? There is no perfect reversing. There is some imperfection left because of 180 degree pulse being not perfect. There will be some artifacts coming into the picture. So how do you eliminate that? This is a very easy thing. What you can do is, you can use this for nullifying all these artifacts or pulse imperfections which are coming because of this one. So what you have to do is simply is, you apply a gradient pulse before 180 and exactly identical gradient after 180. Okay, I'm sorry. So what is going to happen? Gradient before 180, what it will do? It will dephase. That's what we understood. Gradient will completely dephase all the signals, because over the entire sample volume, different slices will experience different fields. So it will become broad signal, or you will not detect any signal. It completely defaces the signal depending upon the strength of the signal gradient. If the gradient strength is very high, then you will make sure that you don't get any signal. And after the 180 pulse, you apply gradient of equal strength and duration. Then what it is going to do? It will rephase the dephase signal. Already it is rephased, it is going to rephase this one. Then what is going to happen? This eliminates the unwanted signal due to pulse imperfection. Okay, whatever is dephased will rephase now and delete all the unwanted signal due to 180 degree pulse imperfection. Then only the refocus pathway is retained. If you apply 180 pulse in between like this, what is going to happen is, after if you are applying a 180 pulse, apply a gradient before and after, equal gradient, equal strength of the gradient and equal duration. Then the dephasing will be such that, then what is going to happen? Only wanted signal will be refocused, all unwanted signal will be completely dephased, and all pulse imperfections will be removed. And we can also do what is called the refocusing in heteronuclear systems. We can use them as refocusing pulses. I tell you what. Consider a sequence like this. I have a 180 pulse on I channel, I spin, and I have a gradient G of equal and opposite, not the same phase, equal and opposite before and after the pulse. What does 180 pulse will do? It will reverse the coherent order. Now let us say I have chosen, let us say I don't choose any coherent order in PI case, it is 0. In the PS case, I can choose coherent order different. When the no coherence order is chosen on I spin, what is the role of 180? It will simply invert. What is the when it is a 0 order? What is the meaning of 0 here? 0 means it is magnetization again along Z axis. It is a Z magnetization plus Z. So what does 180 does? The magnetization which was along Z, it will reverse it. It will make it minus Z. Z magnetization become minus Z now because of 180. Although there was no coherent order chosen, the coherent order P is equal to 0 pertains to Z magnetization. That is what I was telling you. Okay. So it will invert the Z magnetization. What if the pulse is imperfect? 180 pulse is imperfect, it is not correct. Then entire Z magnetization here will not come exactly to minus Z. There will be some residual transverse magnetization left. Some component of the magnetization will be there, and then you can get some components here. Then it generates unwanted transverse magnetization. Exactly. If the 180 pulse is not exactly perfect, the inversion is not 100% proper, then you will generate transverse components. But now Advantage of this, the second gradient of equal and opposite this thing, opposite pulse, opposite strength is equal and opposite. What it will do? It will again dephase the transverse magnetization. You understood? It will dephase the transverse magnetization. Then all the transverse components which are present will become 0. You will not detect that at all. They become unobservable or undetectable magnetization. So the perfect, if there is a 180 pulse is imperfect, if the magnetization which is tilted from plus z to minus z is not proper because of imperfect 180 pulse, then application of the gradient like this just before and after of equal strength, equal and opposite strength, then it will nullify the transverse components and remove all the pulse imperfection. Okay. What did we do here? We have chosen P is equal to 0 for I spin, but I have chosen some different orders are also present here. There are P is equal to plus 1 minus different orders are present here for S spin. Now question is, what will happen to S spin? The gradient G1 and gradient before and after, what it is doing for S spin? 180 pulse on I spin has no effect on S spin. Remember, pulse applied is an I spin. That is what I explicitly I asked you to see that. Here pulse is only an I spin. There is no pulse on S spin here. Absolutely no pulse at all. So as a consequence, since there is no pulse, if there is some coherence present, there is no pulse, I agree. If there is some S spin coherence present, what will happen? The first gradient dephases this, that S spin coherence, but equal and opposite will again rephase it. Eventually, what is going to happen is S spin will remain unaltered, will undisturbed. You understand what I am saying? You apply a 180 pulse on the proton channel, plus Z, now our coherent order chosen is P0. The P0 is the Z magnetization. Z magnetization get inverted with 180 pulse, which will become minus Z. Now, if it is not exactly 180 pulse, there will be some transverse component of the magnetization created. But what you are going to do is, you are applying is another gradient of equal strength, gradient after 180 pulse, then it is going to completely dephase it. That is what it does. Okay, we will remove that. But S spin, whatever may be the coherent order present, does not matter. The reason is, we are not still applying the pulse on S spin. We are applying only an I spin. That will not disturb S spin at all. There is no effect on the S spin. Okay. But nevertheless, the gradient is applying to both, even though I do not apply the pulse on S spin. So the gradient dephases also S spin magnetization. It will dephase S spin magnetization before 180. But then after 180, equal and opposite magnetization is opposite gradient is applied. Then what is going to happen? That is what we understood. The dephasing will get rephased with equal and opposite gradient. Gradient of equal duration and equal strength with opposite sign. If you apply, whatever is dephased will get rephased. And essentially, this has no gradient, has no effect on S spin. It affects only on I spin to remove the transverse component which is created because of pulse imperfection. So this is what the important concept of it. In effect, gradient cleans up the signals due to 180 degree pulse imperfection. This is the important thing for 180 impulse function. How do we remove 180 impulse 180 pulse imperfections? And this is where gradient is useful. Can you remove the phase errors also? How do we remove the phase errors? Okay. What about the, you see, we have been discussing about the coherence order, coherence pathway. What about evolution of chemical shifts or offset, what you call, and J couplings during the gradient pulse? When the gradient pulse is applied, that time, at that time also chemical shifts and J coupling can evolve. Then what happens to that? That gives rise to some errors. They do not get refocused by the refocusing gradients. Chemical shifts and coupling do completely, only the echo sequence it get refocused, but not just like that in all the gradients. So they do not get refocused by the refocusing gradients. What it will do? It will result in what are called the phase errors. Okay, these gradients, because of evolution of offsets or chemical shift and J couplings, it gives rise to what are called phase errors. What to do with these errors? How do you correct it? You can correct these phase errors by what is called a spin echo sequence. You can do that. That's what I said. Spin echo you can utilize to correct all these type of errors, and this is what it is. You look at the simple pulse sequence. It is a 180 pulse. It is like an echo. There is a tau before and tau after, and then there is a gradient applied only after 180 here. And before the gradient, coherent order is plus p. We know 180 pulse will reverses it and become coherent order minus p. Now what I am expecting is the error because of this gradient, phase errors will come. Phase errors will accumulate during the gradient, during the first tau, and it has to be refocused by the gradient, by the spin echo. Now whatever the phase error acquired here, during this time this gradient will completely refocus this one, and that way any phase error if it is present, that can be completely removed. Now another thing, phase error accumulated during first tau is dephased by gradient. It gets further dephased if you apply another pulse of equal and opposite gradient after the 180 pulse. Does not matter. We are allowing it to dephase further, nothing is going to happen. So what is going to happen? All the phase error which are present because the evolution of J coupling and offset during the gradient pulse, they will be completely removed. So these are all important things. How do you eliminate the phase error? Like echo like sequence. Of course you can have the gradient pulse only one or before and after, either of them. Both the methods can be adopted. We have what is called a purge gradient, also called homospoil gradient. This is something which is very often used in many experiments. When we come to that, we will understand when we take one or two example. As I told you, Z magnetization is nothing but the order P is equal to 0 is always unaffected. It is not good. Order P is equal to 0, it will not be affected by anything. To retain the Z magnetization, what you have to do, you have to apply the gradient, then it defaces all the transverse magnetization. You apply a gradient pulse, P equal to 0 is unaffected. P is equal to 0 will not be affected by gradient at all. But if I want to retain only Z magnetization and dephase all the transverse magnetization, what do? Apply the gradient now. Simply apply a gradient, all the transverse magnetization gets rephased. Then Z magnetization alone will be retained. So in many experiments in between, when you are doing, supposing you have a doubt, the transverse component of magnetization is generated for various reasons. It is because of the imperfect 90 pulse or imperfect 180 pulse or anything. Let us say there is a transverse magnetization created, but there is also you have brought back the magnetization to Z axis. You want to retain that. At the same time, you have to nullify the transverse component. You can use this type of purge gradient. This is called homospoil pulse, homospoil gradient or purge gradient. This is also often used in many experiments. Of course, one problem if you do that, it won't distinguish between P is equal to 0 is also for 0 quantum coherence, which we know. P0 is also Z magnetization. It is also for 0 quantum coherence. In many coupled spin more than 1, 2 or 3 and above, you also have 0 quantum coherence. But this may not be able to distinguish these two, but there is a way to select that. So 0 quantum coherence can never be selected by gradients. You have to use phase cycling. So when I come to multiple quantum, if there is time, I will discuss that. But right now remember, this problem will be there for P is equal to 0, especially when you apply, it cannot distinguish the P is equal to 0 quantum, 0 coherent order and 0 quantum coherence both. So another thing what we can do is, very interesting thing we can do. We can do selective excitation and selective inversion, both we can do. These are another one or two applications of gradients that you must understand. This is a pulse which is going to be applied The gradient echo is called a gradient echo. Whatever the gradient applied here, equal gradient you are going to apply on opposite side. It is like 90, 180, 90 echo sequence. This is like this. This is a 180 pulse is coming in between. The gradient echo always ensure that all the magnetization other than the selected spin will dephase. So I can select only particular spin, let us say. I can use soft pulse here. Then what will happen is I can select the particular spin, then I will invert that or selectively excite that and make sure that all other components which are present other than the selected spin will completely dephase. Is possible. These two gradients will dephase all the magnetization other than the selected one. This is very better way of selective excitation. The excitation selective is going to be very clean selective excitation. Okay, and of course, this is another thing which I wanted to say. After this gradient, you apply another pulse. What is going to do? The gradient echo ensure that all magnetization other than the selected one up to till now we know it selects only the selected magnetization, selected spin, and all other things get completely nullified. After that, if you apply another pulse, what is going to happen? This results in very clean selective excitation also, plus addition 90-degree pulse will take the magnetization to minus z axis. So up to now, up to here we know there is a very clean selective excitation because other than the selected magnetization of the particular spin, entire other magnetization gets completely dephased. After that you apply another 90 pulse, you are taking the magnetization to minus z axis. Then what is going to happen? Then you do what is called selective inversion. This is called selective inversion. You can do selective excitation using gradients, very clean selective excitation. At the same time, you can do selective inversion, that is also very clean. So these are all very useful applications. By applying gradients in many experiments we may have to do apply, for example, selective refocusing experiments are there where I want to get the J coupling for a particular selected proton. I need to apply gradient pulses in such a way only that particular selected coherence or selected spin, that magnetization will survive. All other things I can remove it. I can completely clean up these things. Then clean selective excitation I can get. At that time I can use the gradient. Or I want to selectively excite a particular spin, make sure all other spins are inverted. That means there won't be coupling between the excited spin and the inverted spins. I can do that. Then what is going to happen is, that is going to be a very clean experiment. For decoupling selectively we can do that also. We can invert the spins, selected spin, so that it won't couple to other things. There won't coupling can be removed. So like this, lot of experiments can be done. Lot of experiments are possible, and gradients can be applied to various examples. When you apply gradients at various places in various 1D and 2D experiments, this has become nowadays very handy compared to phase cycling. Phase cycling, of course, in some cases we cannot avoid, you have to use it, but then gradient has become very useful technique, application of gradient with number of things you can do. Okay, so I think more about gradient we can discuss, but at the moment I think we have discussed enough. So I will no need to discuss pulse field gradients further. We can keep on discussing, but what basically I was telling you about the pulse field gradient is that pulse field gradient, right from the beginning what we discussed, it creates gradient, it creates inhomogeneity along the z axis and adds to the main magnetic field. The gradient coil is designed in such a way, from the center of the coil upper half is always increasing gradient, increasing field, bottom half is field decreases, and then spins above that gradient, above the center rotates very fast, precesses faster, spins below rotates slowly, And this Z rotation can be reversed by applying a counteracting gradient of equal and opposite strength. So that means another thing what happens is when you apply the gradient thickness is, gradient strength is very large. You can imagine as this slice, there are several slices of different thickness. In each slice, the spins will experience different Larmor frequency. They undergo different Larmor frequency. But within this given slice, they all have the same frequency. But if the gradient strength is huge, sufficiently large, then what is going to happen? The slice thickness become narrow and narrow, and it is like continuous distribution. In the sense, all through the sample volume, the different nuclear spins right from bottom to top, entire RF coil area will experience different Larmor frequencies. As a consequence, you are going to get enormously broad signal which cannot be detected. This is what is called dephasing. Z rotation can be reversed by applying a counteracting this magnetic field of equal and opposite strength. Then you are going to get back the magnetization. Whatever is dephased, you can get back, and this is called rephasing of the magnetization. You can use the gradients by applying before and after the pulse. You can select a particular coherence pathway. You can select the coherence pathway for homonuclear case, and you can select the coherent for the heteronuclear case also. But in the homonuclear case, we took the example, it was 1:2, 1:3, minus 1:1, where one or two examples we took. We could select a particular coherence pathway by looking at the ratio of the gradients. But same thing we did also for heteronuclear case. In the heteronuclear case, what happens? Only thing is gamma is different, but you should not forget one thing. In the heteronuclear case, the total phase acquired along Z axis during the gradient G1 and G2 by both the spins I1 and I2, or I1 and S spin, heteronuclear spin, we will call it S, I and S to be considered, and then find out what is the total spin, total phase acquired, and it should be equal to 0 for perfect refocusing, and then calculate what is the ratio of the G1 and G2. Keeping the duration T1 and T2 identical, you can find out what should be the gradient ratio to select a particular pathway both for I spin and S spin, both during G1 and G2. And also we saw, in addition to that, the gradients can be applied for varieties of application. It is for selective excitation. Clean up this we can selectively excite a particular spin, and there is a transverse magnetization created, that we can remove it also. And 180 pulse inverses, we can, for 180 pulse imperfections can be corrected by applying the gradients before and after. So it will continuously dephase and make sure that imperfection will be removed. And selective inversion can also be clean. If there is any imperfection coming because of that, that also can be removed by the gradients. So like this, number of examples we saw, including pulse gradient, pulse imperfection and removal, selective excitation, selective inversion, everything is possible. But all these things I was trying to give you an example only for the one-dimensional examples, one-dimensional NMR spectra. But these gradients are extensively utilized, and we have number of two-dimensional experiments. These will come very handy when you use it. And then, since I have not introduced 2D, I have not discussed that. I will come back when I introduce 2D. We will discuss more about these things. More, at least one or two examples we will take, how we can choose the pathway by using this gradient. For example, for a DQ of COSY, NOC or HSQC, we can do that. So, we will come to that later. We will discuss all those things in the subsequent classes. So since today the time is coming up, I am going to stop here. With this, we have covered all about phase cycling using pulses, receivers, pulse phase and receiver phase monitor. We can manipulate and get the chosen pathway, that is a coherence pathway selection. You can also do the same thing by gradient dephasing and rephasing, everything we discuss. So we will stop here, come back, and tomorrow and next class I will continue with a different topic. No more phase cycling, that will come back only after 2D. So next class I will see, maybe we can start discussing about NOE or T1, T2 relaxation phenomena, that we will discuss. Thank you.